Swayam Prabha. Digital India. Educated India.
So you try imagining that if you're trying to study it just at Tm, at the melting point, it has become liquid. Slightly higher you may go. So it has become liquid, and then it will be difficult to stir. But if you increase temperature, then for T greater than Tm, it will be easier to stir. So what you said is its fluidity has increased. Okay, and that's why with temperature typically the viscosity of liquid decreases. Okay, this is different than viscosity of gases. Okay. Okay. So this thing is, this is just, again, there are different models. I try to give the simple models for these two things, and just a way to think, because somewhere you should be, you're in the Department of Metallurgical Material Science, so you should be aware of some origins of these properties as well. There are courses where actually, for example, high temperature characterization course, you can take to see how they measure viscosity, and probably will know more about theory of viscosity and so on. So here you see the typical values of so typical values of viscosity. So depending on material, so it can vary from 10 raised to minus 4 to 10. So five order of magnitude it can vary in Pascal second. So you can see that in this case it varies a lot, unlike gases where it didn't vary long. Gas typically 1 to 3, 1 to 5 or 6 if you consider temperature effect, then so 10 raised to minus 5 pascals. So here it goes, so as things like acetone or liquid alkali metals can be close to what you see, maybe 5-10 times higher than the gases. But in general, the liquid will have much higher viscosity, which makes sense. If you are, you can fly your, viscosity is also related to drag. So it's easier to fly than if you are going through, if it is submarine and so on, because you have more distance. Anyway, okay. So this essentially gives the typical values of viscosity. Okay. So you should have some idea on order of magnitude, at least. If someone says how viscous gas is, you should have, it's about 10 raised to minus 5 pascals. And how viscous the liquid is, it's higher than that, but depending on liquids, if it is lighter liquid, something like acetone is 10 raised to minus 4, but if it is something, slag or and so on, so then it's order of 1 or 10, 1 pascal second. Okay, so it's like, think this in terms of weight of an ant versus weight of an elephant. That way you should look. Viscosity also, if it is an order of magnitude variation, you should be able to tell whether it is close to ant or close to an elephant. Okay, that kind of, at least, idea you should have. Okay, so now so we saw that for Newtonian fluid, the viscosity was mu dvx by dy. So viscosity was typically, is proportional to dvx by dy. This can also, this is typically given in terms of strain rate. Okay. So del x, by del y will be strain, and then you do by time, so that becomes a strain rate. Okay. So if for non-Newtonian fluids, typically, all gases and single phase non polymeric liquid follows this, follow this Newton's law, and non-polymeric single phase. It's important to know the single phase. There could be immiscible phase liquids, and then it will be multiple phases. So anyway, or sorry, miscible phases rather. There could be two phase liquid as well. So non-polymeric single phase liquid, generally these two they follow Newtonian fluid, Newton's law, and that they cover wide range of material. However, there are cases where Newton's law is not valid. So no Newtonian fluid. So if it is Newtonian, then if the gradient is if the gradient is 0, then your shear stress is 0. So this is for Newtonian fluid. Okay, and now you can have a positive deviation from Newtonian fluid, and it could be negative deviation. So here you have gamma dot, or you can write as minus dvx. Okay, so there may be cases where it can go like this, or it can go like this. Okay, so this is typically called pseudoplastic, and then there are cases where if you keep applying shear stress, you will not get any motion, but after certain threshold of this tau naught, you start going. Then it again follows linear. Okay, so such fluids are generally known as what we call as Bingham plastic. Okay, so these are some of the non-Newtonian behavior you can expect. Okay, in this course we'll deal with Newtonian fluids, so we are not going to non-Newtonian regimes. Okay, what you would find interesting if you have done a course on mechanics of material, then you would see that the stress strain plot also generally you can have Hooke's law, which will be equivalent to this. And then there are power law and so on. So stress strain in solids also has similar relationship as well. Okay. So let us do some practice problem before we. So which of the following is or are true regarding the effect of temperature on viscosity? So viscosity of gases increase with temperature or decrease with temperature. We have seen liquid increases with temperature or decreases with temperature. So we have discussed this. And shear stress is always non-zero. It's always, this is important. Okay. Okay. Shear stress is always non-zero if fluid is static, if fluid is in motion, or there is a relative motion within the fluid. Okay. So this always is very important. You can look at this graph. So if there is some strain rate, that means that the fluid is in motion, and if it is in motion, then you can see that there has to be okay. So you can answer these things, and so okay. So next we'll look at momentum conservation. Okay. And we'll look at through this example of flow through a circular tube. Okay. Okay. So let us say we are looking at downward flow. Yeah. So before we get into momentum conservation equation, etc., let us first look at this flow. Okay. So to start with, here you have a uniform flow, right? So from this reference line, see length of all velocity vectors are same. So this is a uniform flow. Okay, now let us track this one. This there's a fluid particle that is coming, and it comes and it comes into contact with this static surface. So the this surface of the tube is not moving. Then this fluid has to come to complete stop because of what we have seen is no slip condition. Okay. Similarly, similar thing will happen in this section. Okay. This comes into complete stop, so that the layer next to it will move, but the velocity of that layer will also will change, and rather it will become smaller. Okay. Now, so since the fluid in the vicinity of these walls have slowed down, and let us say this fluid is incompressible. So this fluid is incompressible. So to respect the mass conservation, the velocity at the center has to increase. Okay. So initially, what we can see is slowly, this will be, of course, this magnitude has to be more than that. Now, since this has slowed down, the next layer will slow down, and so on. And so the center velocity will keep increasing, and then something like this will happen. Okay, that is happening from both sides. So after a certain time, this information of this interaction of this fluid at the surfaces will reach to the center line, and once that has happened, then this should not change. Then the flow profile should remain the same. Okay, because the effect of the fluid at rest here has reached to the center after a certain length, and then we have some. So this is symmetric. So don't literally go by my drawing. Okay, so from the moment it enters in this tube, the center velocity keeps increasing, and after a certain time, this remains the same. This becomes large enough, and then so that it can sustain this flow here. Okay. So that once that happens, we call this region as So in the region where this flow starts, we can think of this as developing flow. So there is some entrance region effect that is there, and then once you are in the region where your flow profile does not change any longer, it is known as fully developed region. Okay, so now the velocity at if you take at any r from this here, the velocity does not change as you move in this fully developed region. Of course, when fluid exits this tube, it will change according to the exit condition. Right? For example, if you do some constriction or or it goes into atmosphere, open. So to suit that, then there will be an exit region length as well. Okay. So in another what we have assumed in saying that the fluid is fully developed, and then this remains constant and this remains constant at any r, the velocity remains constant. What we have assumed is the flow is laminar. Okay. You can recall from Reynolds' experiment, that if it is laminar flow and you put a dye here, dye will just travel like this. Or if you put dye here, dye will travel like this. So dye does not mix. So these two layers don't mix, and that is what we are saying, that the flow remains laminar. So we are making some assumptions. So far we have said incompressible. Of course, no slip condition is always there. So and then you have laminar flow, and in our the description of this flow through circular tube, we are only concerned with what happens in the region. Okay. So we say that whatever, let us take a section, we'll say we take a section L of length L, but then this length L is in in the fully developed region. Okay. Before we go to this, there are few things we should make sure that what do we want to know. Okay. Now that we are looking at fully developed flow, incompressible flow, laminar, fully developed laminar incompressible flow. What we want to know is few things. Okay. First of all, in this developed flow region, of course, you want to know that thing for entire tube. In this region, what will be the pressure drop? Okay. So if the pressure here is P1, here is P2, what will be the pressure drop? No, or pressure gain, whatever. In this case, we are going in this direction. Rather, it will be easier to think if you think you have certain pipe like this, or it can be horizontal. So if you want to flow certain amount of fluid, then what should be what should be your supply pressure, right? If you already know this pressure, so what should be the supply pressure? We want to know per unit length and so on, because remember, from the overall energy balance, this depends on there is some mechanical energy or potential energy loss or so, because of somewhat on mechanical energy loss, rather we can say because of loss to friction. Okay. There's relative motion between fluid layers, and then there's also this friction. So we want to know what should be delta P. Okay. Let us say we maintain delta P, then we want to know what should be in some cases you may not have control over delta P, but what you can control is tube size. So instead of this large, should we take a smaller diameter tube, and so on. Sorry for the bad drawing. So you want to know how this will change with diameter. So tube size. Okay. So these two things you want to know. For given pressure drop, what should be your diameter, so that how you can size the tubing. Or if you know the tubing size, then what should be your pressure drop, supply pressure. Okay. For a given flow rate. So if you want to flow water at certain kg per minute, so what should be your pressure drop? Or if you know the pressure drop, what should be your size of the tube? That is one thing. Second thing, the pipe material itself. Try imagining that you have some very thin walled plastic pipe, and if you are trying to flow more and more fluid, there will be some there is some shear stress here, and so you need to select material so that can sustain the shear stress, and then so on. Okay. So that becomes you can those relationships are available in if you do mechanics of materials course. So what is the pressure or stress in the direction? So imagine if you are trying to blow through a tube, and if you press one end, and it may rupture if it is thin or weak material, right? So we want to know what is the wall shear stress. Okay. So this gives you some perspective on how we should approach the problem. Okay. So now we do the momentum conservation. Okay. Let us make one more assumption. So we have assumed incompressible, laminar, fully developed, and let's add this to this steady state. Okay. So we want to write momentum conservation equation. Before that, let us first do this. We always do this. Two of them: mass conservation and momentum conservation. First, let us do mass conservation. Okay. So we start by selecting a volume element. This is tube. So cylindrical coordinate is our natural choice. So this is the large tube, and inside that this is your R. let's do it here. So this is R and then this is Z. Okay, so here you have Z equals 0, here you have Z equals L, and here you have R equals 0. So we take, you know, this is R and then this is the thickness over here is, you know, some dr, or you know, start by dr or delta r to start with. Does not matter. Okay, so the for you know, for flow, you know, this is essentially a cell we are looking at. You know, this is a cell. So this is also known as, you know, we call it cell momentum balance and so on. So this is a cell. So the cross section area of the cell of the cell that we have considered is what? 2 pi r delta r or dr, right? Okay, so if we see how much mass is, you know, or mass of fluid is entering here, so mass conservation will be mass in equals mass out, because we are at steady state. Okay, and we have assumed incompressible, so rho remains constant. Area over here and over here, you know, the cross sectional area is same, 2 pi r dr, and then this will be v, you know, vz, whatever is coming in this z direction at z equals 0 should be equal to, density is same, 2 pi r dr vz z equals n. Okay, so these things are same. So what we can say is vz at z equals 0 should be equal to vz at z equals L. Okay, so this we have seen even in the when we are describing the flow, we also said that, you know, at any point this velocity at a given r does not change with the length in the fully developed region. Okay, so okay, so now let us do the momentum conservation. So as usual, what we write is momentum in, like any conservation equation, minus momentum out, and there is no generation term, etc., and it is steady state, so this will be 0. Okay, so now our main task becomes to identify what all things, you know, what all forces are contributing to this momentum. Okay, you rather rate of momentum and so on. Okay, rate of momentum is essentially the force. So what kind of momentums are involved in this case? So first will be, you know, advective term, advection term. No, that is because of motion of bulk fluid, you know. So if you write this advection term, it should be, you know, mass times velocity, where mass you can give, you know, rho a, and we know at v, if you write whatever enters at vz, this is mass, and then velocity will be one more vz, where your area essentially is rho. So rho area will be 2 pi r delta r, and then vz. So if you write in minus out, then this will be rho 2 pi r delta r vz square at z equals 0 minus vz square at, you know, rather you write vz, yeah, so vz square at z equals L. So but from our mass balance, you know, mass conservation, we know that these two terms are essentially same. So this does not contribute to any whatever is momentum coming because of bulk fluid motion is just going out. Okay.